Hello, welcome back to Math with Patrick. Today is March 8th. We have problem number 67. We're going to solve it together. So let's find the ratio of the larger circle to the shaded region. So just talking about ratios in general, if I have something that's like 4 to 1, you could think about it as like 4 circles for every square that I have. In the case of area, we could get a scenario that looks like 3 blocks to 1 block. And so this is going to be a 3 to 1 ratio. And here, since the answer is today's date, it looks like I'm trying to prove that we have an 8 to 1 ratio, or I have like 8 objects all next to each other, and this is going to be compared to just one object. So it would be enough to somehow try to do this like geometrically, to like take this shape right here, I can copy and paste it right there. I'm guessing that this is the center of the circle. So then I could, put another copy here and another copy there. And already I have like 4 of my shapes. But then it gets a lot harder to just try to fit another semicircle in here. Like maybe I could fit it like that, but then I'm starting to create weird shapes that don't really conform to semicircles anymore. So this like naive approach, I would say, of like trying to just fit this shape in the big one kind of stops working. Let's introduce a variable. Sometimes a good idea when you're working with lengths and you're not quite sure what the lengths are. Let's just say that this distance right here is, why not little d for diameter? And we can compare it to capital D for the larger diameter of the larger circle. And if you notice here, if you agree with me that this is the center of the larger circle, then we can say that 2 times little d is equal to the capital D, the big diameter of the bigger circle. If we try finding their areas, because we're finding the ratio, well, it doesn't say that, ratio of the larger circle to the shaded region. The shaded region is an area, so I'm pretty sure that we're working with the area of the circle. It doesn't really say area or circumference, but let's just assume it's area. So area of the big circle is going to be, well, just the formula says pi r squared. And this r is coming from the radius of, well, the big circle. Though if you notice, its radius is actually the shorter diameter. So here, for the area of the big circle, I'm going to write pi little d squared, because this is the radius of my big circle. And then the area for the small circle is also going to be pi r squared, but here my radius is going to be different. Just to differentiate these r's from each other, why not call it the big radius and the small radius? The small radius will be half of my small diameter, so I'll write pi diameter over 2 squared. Okay, and I need to find the ratio of the larger circle's area, probably, to the shaded region's area, probably. So the shaded region is actually going to be half of the area of the small circle. So maybe I'll do X and I'll color it in blue just to kind of match this color from over here. Let's say that X is going to be equal to half of the area of the small circle. And so that will be half of pi times little d over 2 squared. Nice. So now I can compare the ratio of the larger circle, the area of the larger circle, which will be area of big circle, compare it to the area of the shaded region, which is x. Doing some substitution, that's going to be pi d squared compared to 1/2 pi d over 2 squared. For starters, the pi's cancel out. So whenever you have a ratio, you can kind of think of it as a fraction. For example, if we have a group of 8 dogs and 6 cats, you can think, at least in terms of ratios, this is the same as saying for every 4 dogs, you have 3 cats. You could scale it down a little bit more if you want, 2 dogs for every 1.5 cats. But that gets a little bit weird, especially if you're counting discrete like animals, like, this one right here. I really don't want to see what half a cat looks like. So when we're working with ratios, you can find common factors on the left and right sides. Here I'm dividing both of these by 2, and it's still considered to be an equivalent ratio. So here I'll divide both sides by pi, effectively just getting rid of that pi factor. So I get d squared compared to 1/2 d over 2 squared. Now when multiplying fractions, I'm looking here. This squared says d over 2 times d over 2. Just like the general procedure is you can multiply across. So this is the same as d squared over 4. So I'll write that here. I have d squared compared to 1/2 times d squared over 4. This is the same as d squared compared to 1/8 d squared. And kind of like how I was saying earlier, where we don't really want like halves to show up in our ratios. I mean, in terms of having cats, don't want to have cats. We want to have whole cats. Right, Quill? Anyways, same kind of issues happening here where I don't really want a fraction in my ratio. So instead of like dividing out common factors, you can also scale it back up and multiply by the same number on both sides of your ratio. And so if I multiply both sides by 8, I'll get 8d squared, which is compared to d squared. And this d squared actually doesn't even need to be here, kind of like how the pi's go away, so can the d squareds. So I have a ratio of 8:1. That 8 is today's answer, so I'm going to put a box around it. And let's just go back up to the top and make sure that this 8 makes sense. This is saying that I could stick 8 of these semicircles in my big circle. And I don't know, maybe you could try counting like 1, 2, 3, 4. I guess you can convince yourself that 2 are down here and 2 are up here. And before you go, I just want to show you something, that it doesn't actually matter that we were dealing with semicircles here. It could have been any shape. We could have actually worked with like a blob like this and had another blob in the middle and halved that blob. And so thinking about a scale factor now, if I reduced the length by half, so I'll say reduced length by half, you can take that scale factor and square it to get the reduced area. So I will reduce the area by 1/2 squared, or in other words, I'm reducing it by 1/4 or by a factor of 4, whichever way you want to think about it. And if our blob were 3-dimensional, then I would reduce the volume by a factor of 1/2 cubed. Because that cubed there is for the 3 dimensions, because now we're thinking 3-dimensionally if it's with volume. So it doesn't matter that it was a circle. It could have been a square. It could have been a Nickelodeon splat, like a area or a shape with an area who doesn't have like an area formula, or that doesn't have an area formula. And no matter what, if you change your scale factor by, say, ×2, then the area will go up by 4 and the volume will go up by 8. If you have something like a Rubik's Cube and you go from 1 to 3, so you increase your side length by a factor of 3, well, you could probably count out and figure out that your volume goes up by a factor of 27, because that's 3 cubed. And this works for any shape. Doesn't matter if it's a circle or a blob or a cube. So hiding behind this problem is a little lesson about scale factors. But overall, if you're able to work with fractions and ratios, you can figure out that the ratio here is 8:1. 8 being the bigger circle and 1 being this smaller semicircle. So that's it for me today. I'm all done, and I'll see you tomorrow.